we have already seen that most polymers display the viscoelastic behavior. So, in this course we will be limiting ourselves to only the linear viscoelastic models. So, there are two different approaches to analyze the stress and strain. One is using the differential equations and the other is using the integral equations. So, we will be looking at both of them first by looking at the differential equations, and later we will also look at the integral form of solving these stresses and strains. But today's video will take a detour, in the sense like we will first focus on the mathematical preliminaries which are required. We will focus on the mathematical preliminaries which are required for us to help develop these equations for the stress strain relations and as well as to solve those equations. So, in today's lecture we will look at unit step functions. Unit step functions are something which we have already seen when we discussed about creep loading as well as the relaxation test. So, in creep test we said we are applying a step stress input, and in the relaxation test we said we are applying a step strain input. So, these can be represented using this step function which is a discontinuous function. The derivative of this unit step function is something called as the Dirac delta function. We will look into how we represent it and what are the few interesting properties of it. Later when we develop our differential equations, it is more convenient to solve them if we transform it into the Laplace domain. So, we will also look at the preliminary definitions of what are Laplace transform and few basic formula which we will be frequently using. So, bear in mind we are not trying to explain all the details here, but it is basically a recap if you have already have seen these, or else it is a quick introduction to these topics. It is suggested that one has to go back to a mathematics book and read or practice a little more, so that you are more comfortable with these mathematics. Okay. So, now let us start with the unit step function. The other name to the unit step function is Heaviside function, and it is represented with h of t, meaning t is a function of time and h is represents the Heaviside function. But now let us look at how it is represented. So, on the x axis is time, which we represent using t, and on the y axis is h t, right. So, we said the way to represent it is through a step function occurring at time t equal to 0. So, let us choose another color to represent that, something like that. So, at times less than t equal to 0, the function value will be 0, but at time t equal to 0 it suddenly increases to unit, and then after time t equal to 0 it again remains constant at the value 1. Okay. So, the way we write this in equation form is h of t, we will say it is equals to 1, we will start with 0 when the time is less than 0, and it is 1 when the time is greater than or equal to 0. So, it can take two values depending on what is the time we are looking at, but it is not necessary that this step is always at time t equals to 0. We can also have a step when it is, let us say, at an arbitrary time. So, let us say we say that this step occurs at some time t1 somewhere here. So, which means before this time t1 the response is 0, but at time t1 it suddenly increases to unit, and after time t1 it remains constant. So, we are talking about time t1 and here it is time 0. and this value is 1. So, how do we write it now? So, with this we represent as h of t minus t1. The value is 0 when the time is less than t1 and it is 1 when the time is greater than or equal to t1. Okay. So, now let us look at previously we discussed about the creep loading as well as the relaxation loading. Let us see how we can use this Heaviside function to represent those loads. First let us discuss about creep load. How do we represent creep load? By figures, the x axis is time t and the y axis is the loading or the input for the creep is the stress. So, we say the loading is constant at time t equal to 0, we have this load applied which is sigma naught. So, how can we represent this? Using the Heaviside function we can now say the stress applied sigma t is sigma naught times h of t. H of t or the Heaviside function takes care of the discontinuity at time t equal to 0 and this sigma naught takes care of the amplitude of this loading. Okay. I could as well say that this creep loading happens not at time t equal to 0, but at a later time, let us say t1. So, let us say at time t1 we say we apply this creep load. So, then there is a instantaneous increase in the load from 0 value to sigma naught and then it remains constant. So, again we are talking about stresses. So, this is sigma naught is the applied stress and it is applied at time t1. So, how do we represent this load? We represent it as sigma of stresses at time t is sigma naught times h of t minus t1. T minus t1, h of t minus t1 takes care of the step function occurring at time t1 and sigma naught takes care of the amplitude. So, similarly, let us also look at relaxation load. So, in relaxation loads we said the input is strain. Strain will represent at epsilon of t. At time t equal to 0 we said we apply a instantaneous strain epsilon naught and after time t equal to 0 it remains constant. So, how do we represent this? Epsilon of t, the strain at any time is epsilon naught times h of t. And similarly, if we are talking about applying this relaxation load at any other time arbitrarily set say t1, so now we can write the input load epsilon of t is epsilon naught times h of t minus t1. Okay. So, now we have seen what are the definitions of this unit step function or the Heaviside function and how we can use it to study or represent the creep loading or the relaxation loading. So, before we move on, let us also discuss about what happens in the proximity of time t equal to 0 for the unit step function. So, in other words, I am interested to know what happens if the time is slightly left to 0, means it is not exactly at time t equal to 0, but slightly infinitesimally to the left of time t equal to 0. What will that value be? That value will be 0 because we are still yet to come to this step. And what is the Heaviside function value for just to the right of this time t equal to 0? So, we are talking about just infinitesimally increment in the time from time t equal to 0. That is when we have this value as 1. So, it is important to note this 0, minus and plus represents whether we are to the slightly left or slightly right to the time we are looking at. Okay. But let us also look at how can Heaviside function be used not just with step functions, but some arbitrary functions. So, let us say we have a sinusoidal wave. So, let us say the x axis is the time and the y axis is the function f of t. It could be any function. For example, now I am taking a sinusoidal wave. So, now let us see what happens when we multiply this function f of t with the Heaviside function. So, now we are talking about a new function f1 of t, which is f of t times h of t. So, now let us see. So, the x axis is time and now the y axis we are plotting this new function f1 of t. Since we multiply this function with the Heaviside, what happens when time is less than 0? The response is 0 because h of t values is 0, 0 multiplied by any function will anyway give 0. So, to the left of time t equal to 0 there is no response, but what happens beyond time t equal to 0? The h of t value, the Heaviside function value will give you 1 and that is multiplied by the function f of t. So, whatever function we have f of t, that will represent the same even when we look at the right side of the time t equal to 0. So, what we have established is we have shown that what happens if you multiply a function with a Heaviside function. So, we are only focusing on part of a function. Yeah, of course, here I could also have defined another function where instead of starting at time t equal to 0, if it is time t equal to let us say t1 is equal to let us say pi by 2. So, what happens then at time t equal to pi by 2, we know the sinusoidal function value will be 1. So, we will start from this top point. So, there will be an instantaneous increase in the function value f2 let us say, and then we will continue to have this sinusoidal wave. Now, let us move to the next topic where we discuss about the derivative to this unit step function. So, which is the Dirac delta function represented as this delta times time. So, now first look how it is represented. So, the x axis is again time and the y axis is this delta of t, which is the Dirac delta function. And we already defined this as derivative of the Heaviside function. Okay. So, what happens to the left of time t equal to 0? Time left of time t equal to 0, let me also plot the Heaviside function, which will help us to better view this. Okay. So, this is how the Heaviside function is. So, to the left of time t equal to 0, we have seen that the Heaviside function value does not change. So, even in the Dirac delta function the value will remain at 0. Okay. Now, let us focus on what happens when time is greater than time t equals to 0. We see that the value remains, Heaviside function value remains at 1, which means again the slope is 0. But now the point to be asked is what happens at time t equal to 0. At time t equal to 0, we have seen the Heaviside function value instantaneously moves from 0 to 1. So, the way it is represented in Dirac delta function is by a spike. Let us say okay. So, let us say this small window is defined by some epsilon. Epsilon is a very small value or an infinitesimal value, then the height or the amplitude of this will be 1 by epsilon. So, what happens when this infinitesimal value epsilon approaches 0? When this epsilon approaches 0, then 1 by epsilon will approach infinity, which means the way to write this function is it approaches infinity when time t equal to 0 and it is 0 when time is not equal to 0. So, this is the definition of the Dirac delta function, saying that it is infinite at time t equal to 0 when the Heaviside function load changes from 0 to 1, but every other instant the Dirac delta function takes a value of 0. So, it has another interesting property saying what is the area under this curve. So, or in other words, what is the value of the integral of Dirac delta function times dt going from minus infinity to plus infinity. What do you think this value will be? The way we have defined this spike is saying that the width is epsilon, which is an infinitesimally small value, and the height is 1 by epsilon. So, the area under this curve is 1. So, this is a very important property because we will see later that it will be used to represent the singularity. So, Dirac delta function helps us to define a singularity. And we have seen that the integral or the area under this curve is unit. So, similarly we can now define what happens when we are talking about at arbitrary time t1 we have this value going to infinity. So, we are now talking about Dirac delta function of t minus t1. So, it will be derivative of the Heaviside function h of t minus t1 with respect to time. This will be again, it will be infinity when time t equals to t1 and it will be 0 at time is not equals to t1. And how does that look like? This is this Dirac delta function delta of t, we are talking about time t1. So, we will have the spike at time t1. So, instead of having it showing with an epsilon, I could simply show it as a vertical line as well, saying that at time t equals t1 this amplitude is going towards infinity. Now, let us look at a unique property of this Dirac delta function, where we talk about the integral of a function f of t multiplied with the Dirac delta function delta of, let us say, t minus t1. So, which means we are multiplying with a Dirac delta function where that spike happens at time t equals t1. And the integral limits can again be minus infinity to infinity. So, even if you look at it visually, So, let us say on the y axis we will first show the Dirac delta function with a spike at t1, and let us also show an arbitrary function f of t. So, let us say we are talking about an arbitrary function, and then we also define this Dirac delta function. Okay. So, what will happen at times other than t1? So, at times other than t1, our Dirac delta function will give a value of 0. So, 0 multiplied by any function value will anyway be 0. So, it does not come into this integral. What comes into the integral is what happens when time t equals to t1. At time t equals t1, we have a function value of f of t1, and since we are talking about the integral, we know when we have the Dirac delta function value at the integral, the area under that curve is 1. So, it is multiplied by 1, or in effectively what we get is the function value at time t1. This is called the shifting property. Shifting property of the Dirac delta function. Okay, we will see later where we will use this to solve some of the equations. Okay, we have seen the step function as well as the Dirac delta function. This should be good enough to at least talk about the creep load and the relaxation load, and when there are differentials involved, we can invoke this Dirac delta function. Now, let us move into, we said when we talk about viscoelastic models, either they can be represented as a differential equation or they can be represented as an integral equation. But when we have these differential equations, it is becomes easier if we solve them in the Laplace domain. So, let us quickly look at what are Laplace transforms and what are the equations and how do we solve them. So, Laplace transforms, let us first write how is it represented as. This is the Laplace of f of t, the function. This can also be written as f dash of s. So, whenever we have Laplace, the other way to represent Laplace is f of s. These are two notations for the same thing, Laplace. But now let us look at the definition of this. The definition is we have an integral from 0 to infinity of f of t, the function, times e power minus st times dt. So, sometimes the limits of the integral can also be written from minus infinity to infinity, that is also correct. So, with this definition, let us look at one or two examples so that we feel more comfortable about what we are discussing about Laplace transforms. So, let us say we are talking about Laplace of a constant c, that we now write the integral 0 to infinity the constant times e power minus st dt. We can take the constant out of the integral, and the integral formula for e power at we know. It is simply e power at by constant a. So, here when we do this integral, we get this e power minus st by minus s. This needs to be evaluated at the limits infinity and 0. So, c, let us take this constant out by minus s, and now let us apply this infinity to this e power minus st, then it will be 1 by infinity again, minus e power 0 will be 1. So, what we get is constant c by s. So, Laplace of a constant is C by S. Similarly, let us look at another example. Let us say now we are looking at Laplace of e power at. So, let us apply this integral formula, then we can write it as integral going from 0 to infinity, the function is e power at times e power minus st dt. So, when we have two exponentials, the powers can be added. So, now we can write it as e power minus of s minus a times t dt. So, again we use this formula of integral of e power at, by which we get e power minus of s minus a. The constant now is minus of s minus a, and the limits are from 0 to infinity. So, when we substitute t with infinity, first let us take out the constant, which is 1 by s minus a with a negative sign, and then what is left out is when we substitute this infinity for time, we get 1 by infinity minus e power 0, which is 1. 1 by infinity is 0, so this will end up as 1 by s minus a. So, now we have seen that Laplace of e power at is 1 by s minus a. These are just two formulas to get us more comfortable with applying these Laplace transforms, but of course you can refer to any standard maths textbook to see the derivations or the formulas for many others. But now what we will do is we will look at some commonly used formulas which will commonly used in these viscoelastic problems. So, let us talk about few functions f of t, and we will look at the Laplace of this function, which is also written as f dash of s. So, we already looked at for constant what we get. For a constant we got it is 1 by s. For function value of t it is 1 by s square. For function value of e power at we got it as 1 by s minus a. Now, if we consider sine of omega t, omega by s square plus omega square. For cos function, the Laplace transform is s by s square plus omega square. Let us also look at the Heaviside and the Dirac delta function. The Laplace function for Heaviside function h of t is 1 by s times e power minus a s, and a should be greater than 0. Laplace transform for Dirac delta function is we do not have this 1 by s like in the previous equations, we simply have e power minus a s, and again a should be greater than 0. So, these are the normal functions, but we will also look at what happens if you are looking at a derivative of a function. So, the Laplace of f dash of t, so which is the first derivative of the function f of t, is given as s times f of s minus f of 0. So, similarly I can also write Laplace for the second derivative f double dash of t which is the second derivative of the function f of t, is given as s square times f of s minus s of f of 0 minus double derivative evaluated at time t equal to 0. So, what we see is especially the last two formulas. The last two formulas say if we are considering the Laplace of a derivative, we end up with an algebraic expression, because in the formulas the Laplace transform domain we see algebraic expression and we do not see these derivatives anymore. So, this is helpful because we said the viscoelastic behavior can be represented using differential equations. So, when we take these differential equations and look it in the Laplace domain, these differential equations will transform into algebraic equations. So, once you do the algebra and simplify those equations, then we again do the inverse transform and come back to the time domain. So, usually not for every problem, but for most standard problems, it so happens that when you go to the Laplace domain, the equation gets simplified, and with the standard formulas you can come back to the time domain using the inverse Laplace transform. This is the reason why we are looking at Laplace transforms as an introduction before we discuss about those differential equations. So, to summarize what we discussed in this video is, we started by discussing the unit step function, which will help us to define creep load and relaxation loads, and then we also discussed about the Dirac delta function, which is the derivative of the step function, and later we also discussed about the Laplace transforms. We started by showing you the definition of a Laplace transform using an integral, and then these are the standard formulas we have for Laplace transform, which we regularly come across when we are solving these viscoelastic problems. And finally, we said the major reason why we are interested in Laplace transforms is because it helps us to transform these differential equations into algebraic equations. Once we simplify, most often it happens that we can again do the inverse transform and go back to the time domain. Okay. In the next class, we will be looking at those equations to start with the linear viscoelastic behavior. See you then. Bye.